The most reliable method for determining the age of an object is called radiometric dating, and it relies on careful measurements of a solid object's proportions of various atoms and isotopes. Imagine that you have found a rock, such as the meteorite shown here. Radiometric dating allows us to determine precisely when the rock solidified into its current form, which is the time when its atoms became locked in their current positions. The method works because some isotopes are radioactive, which is a fancy way of saying that their nuclei sometimes undergo a spontaneous change, or decay. Decay changes one element or isotope into another. For example, the radioactive isotope potassium-40 can decay to become argon-40 when one of its protons changes into a neutron, emitting an electron in the process. We say that potassium-40 is the parent isotope, and argon-40 is the daughter isotope. Laboratory studies show that any significant amount of a radioactive parent isotope will gradually decay into the daughter isotope at a rate that we characterize by a half-life, meaning the time it takes for half of the parent isotope to decay. This cartoon shows the idea. The red dots in this rock represent radioactive potassium-40. In this case, we assume that the rock did not contain any argon-40 when it solidified. Over time, the potassium-40 gradually decays into argon-40, shown in yellow. After one half-life, half of the original potassium nuclei have become argon nuclei. Half the remaining potassium nuclei then decay by the end of the second half-life, leaving only 1/4 of the original potassium nuclei still intact. Half of these then decay by the end of the third half-life, and so on. Now consider this question. How much of the original parent isotope remains after 4 half-lives? Is it 0, 1/8, 1/16, or 1/32? The answer is C, 1/16. To see why, notice that 1/8 of the parent isotope remained after 3 half-lives. Half of this 1/8, or 1/16, will decay to become the daughter isotope during the 4th half-life, leaving the other 1/16 still as the parent isotope. Every radioactive decay process has a unique half-life that can be calculated from the decay rate measured in the laboratory. The half-life for the decay of potassium-40 into argon-40 is 1.25 billion years. So this graph shows how the proportions of potassium and argon change with time in a rock. The horizontal axis shows the time since the rock formed in billions of years, and the vertical axis shows the fraction of nuclei for the two isotopes. The red curve for potassium-40 starts at 1, meaning that 100% of the potassium-40 nuclei are intact when the rock first forms. The blue curve starts at 0 because there is no argon-40 at that time. As time passes, the amount of potassium-40 goes down while the amount of argon-40 goes up, so that after one half-life, or 1.25 billion years, the two isotopes each represent half of the original potassium nuclei. By the end of 2 half-lives, or 2.5 billion years, only 25% of the original potassium-40 remains, while the other 75% has turned into argon-40, and so on. You can now see how radiometric dating works. Suppose you find a rock and measure that among its total potassium and argon atoms, only 12.5% are potassium-40, while 87.5% are argon-40. You can then conclude that the rock is 3.75 billion years old. We can be confident in ages determined through radiometric dating, not only because the method is so well understood, but also because it can be cross-checked by measuring more than one set of parent and daughter isotopes in a rock, and sometimes in other ways. For example, some archaeological artifacts have dates printed on them that agree with ages measured through radiometric dating. In the case of our solar system, the 4.5 billion year age we measure through radiometric dating of the oldest meteorites agrees with an age estimate based on careful study of the Sun. While the details of dating a particular object can be complex, there is no scientific doubt about the general validity of the method of radiometric dating.